Bonjour, welcome to Wahsa Distance Education Center's radio Zoom classes. This is MBF3C, grade 11 college math, and I am Bronwyn Slate. Today's lesson is pre-recorded, so you can't join live. However, you can listen at 91.9 FM or Bell Express View channel 972. Our classes are scheduled on Monday through Thursday, 11 a.m. to 12 p.m. And we are now in week 8 of our 9-week course. At this point, should be submitting work for marking. The questions in your booklet marked with a pencil icon are not questions to submit for marking. They are the support questions for practice. You decide which ones and how many of them to do. If you're understanding a concept, feel free to skip questions. And if you need more practice, let me know and I can send you more work. The answers are in the back of your book, so check your work. However, there have been mistakes found. So if anything isn't lining up, let me know and we can check to see if that's an error. The key questions, the ones marked with a key icon, are the ones to submit for marking. Please do all of them, show all of your work, your steps, and your thinking so I can give you credit for all of your understanding, and also so I can see if you are making errors, where those errors might be happening and why. There are 3 methods to submit your work. The first is to scan and send your work in electronically. You can scan your completed work with a smartphone, either through the iPhone's Notes app or the Android Google Drive app. If you don't have a smartphone and you just want to take pictures, that's fine as well. Please then either email your work to studentwork@nnec.on.ca and CC it to bronwyn.slate@nnec.on.ca, or send it through Facebook Messenger to bslateWahsa. The second method is to drop it off in Silico. We have an outdoor mailbox at 74 Front Street. We're the big red building next to the post office. We have a small white mailbox next to our side entrance. We currently are working remotely, so it may take me a couple of days to get your work, but I'll get it back to you as soon as I can. Third method is to hand it into your DEC. Your DEC can then either send your work through the Express or fax it to 807-737-1732 or toll-free fax 1-800-463-7852. If you have any questions or concerns, please contact me. This is why I'm here. My email address is bronwyn.slate@nnec.on.ca. That's spelled BRONWYN.SLATE. You can also reach me on Facebook at bslatewahsa. You can call the main office and leave a message for me and I'll return your call. The number is 807-737-1488 or toll free 1-800-667-3703. My office hours are Monday through Friday, 8 a.m. to 2 p.m. And I'll get back to you as soon as I can. You'd like to connect with me through social media? My Facebook and YouTube channel are both under the name bslatewahsa. You can friend me on Facebook and subscribe to my YouTube channel, and then you'll be notified every time I upload one of our lessons. All of our radio Zoom classes are uploaded shortly after airing. There are also short videos on my YouTube channel that explain common errors and confusing concepts. So that's a great place to check out if you're struggling, if you're struggling with a concept. It's a good place to help you out. Math is an incredibly visual subject. So connecting with the videos is going to set you up for the most success, either watching it live through Zoom or the replays on YouTube. If you don't have reliable internet to do either of those, let me know and I can send you a USB key with all of our recorded lessons on it, and then you still have access to them. All right, today is day 29 of our course, and we are looking at lesson 19, which is theoretical probability. Our learning goals are that at the end of this lesson, you can say, I will be able to calculate the probability of something happening. I will understand probability terminology, and I will be able to represent probability in a variety of ways. Success criteria are, you know that you have met learning goals because you can say, I can calculate the probability of a desired event. I can use probability terms accurately, and I am comfortable with probability representations in various forms. All right, let's activate our brain with some mental math. I'm not a fan of the classic mad minutes where we do as many arithmetic facts as we can within a minute. They didn't set us up for success or build confidence. So instead, we focus on developing strategies that we can transfer to various situations and that are based on our number comfort and using friendly numbers for ourselves. Today, we're going to be looking at the question 28 plus 47, and we're breaking it up by place value. So with 28 plus 47, what that means is that we're going to do 20 plus 40. Sorry, not sure what I'm writing there. Try that again. 20 plus 40 and 8 plus 7. Well, 20 plus 40 is 60 and 8 plus 7, well, 7 doubled is 14 or 8 doubled is 16. So 8 plus 7 is going to be 15. And then we add the two together and we get 75. This is often how I do this sort of thing in my head. I know that 8 and 7 is 15. I know 20 and 40 is 60. So 60 plus 15 is 75. All right, mine's on. Let's engage in some prior learning. So we need to remember about decimals, fractions, and percentages when we're dealing with probability. So the key is that there are different ways of showing the exact same value. So 1 over 2 is equal to 0.5, which is equal to 50%. They are all half. So in probability, we use these interchangeably depending on the situation. And it's really just important to remember that the fraction and the decimal and the percentage are all the same, though they look slightly different. And so being able to convert them back and forth is really important. All right, so let's dive into some new concepts about probability. So when will you use this in real life? So we are strengthening our ability. Critical thinking is key to pretty much everything that you're going to do in life, whether it is to run a business or be an employee, to be a parent or a caregiver. We are constantly presented with problems and need to think critically in order to figure out how to solve them. So probability is all around us. We have a few visuals to look at. We have one that is from the Weather Network, which shows the temperature for the next 14 days and the precipitation in both the day and the night. Of course, we don't know if this is exactly going to happen, but we're forecasting. That's what forecasting means, is that we are using probability based on historical trends of what is realistic for this time of year, as well as what has been happening currently in the last few days and weeks. So, and looking at weather patterns and movement of air currents and all sorts of things like that. There's lots to go into it, but it's all about probability in terms of how likely this is going to happen in order for us to predict the weather. A second image that we have is about sports betting. So pretty much any betting, but particularly looking at this graphic is about sports, I think football, but I don't know. Is so how whenever you do any sort of gambling, it's based on probability in terms of what is likely to happen, what is not likely to happen. If something is likely to happen, then you're not going to have very high odds because it's fairly certain it's a safe bet. But if something is unlikely to happen, it's going to have higher odds, and you are more likely to win more if you bet on that because it's less likely to happen. I'm not saying gambling is a great choice, but that is what it's based on. Third, we have this lower image that talks about risk analysis, and if it's low, medium, high, very high, or extreme. So this is how, when you're investing money within companies or banks, we use analysis also in terms of medical care, risk analysis based on your demographics, and things are all based on probability in terms of if this is a lifestyle that you live, if this is your genetic history, then this is the probability of this medical situation happening, And these are the outcomes, how risky it is. So all of that is also based on probability. And then finally, we have a graphic of a Google map that's talking about commuting hours. So if you're trying to travel, this image is from Thunder Bay. If you're trying to travel from one place to another place, it predicts how long it's going to take you and where there's going to be congestion based on past patterns and past projections. So they don't know, obviously they can't predict this at this one particular time, but in the future, but they can, based on previous experience on the day of the week, on the time of day, they can predict it based on the probability of it happening again in terms of what has happened before. All right, so let's make sure that we have some vocabulary that we know what we're talking about is all the same. So this is on page 21 of your IEL booklet. So probability, just to define, is the chance that a particular thing will occur. It's measured as a ratio out of the total possible outcomes. So there's always two parts in a probability statement. Even if it's in a percent or a decimal, you might need to translate it, but how much, what you want to happen out of all the possible things that could happen. So it is a range between 0, which is impossible, it's not going to happen at all, and 1, which is certain. So probability is always measured as a decimal or a fraction or percentage, because it is in that range from between 0 and 1, or 0% and 100%. If it's between 0 and a half, it's not likely to happen. If it's between half and 1, it's more likely to happen. All right, so more terminology. A successful result is that what you are hoping to measure or achieve, and this doesn't have to be a positive outcome. So if you think that rainy days are not a good thing, but you are trying to say what the percentage chance that it's going to rain. So your success is that it rains, that's what you're measuring. And so even though you don't think that it's great that it's raining, what your success is defined as is that it's raining for your probability. So that's really key to pay attention to, is that it's not have to be, a success doesn't mean that it's something that is actually positive or successful, it's just what you're measuring. Trials are the number of times an action is repeated to complete an experiment. So how many times you do something or measure something. Sample space is the collection of all possible outcomes of an experiment. So everything that could happen. Outcome is a specific and possible result from a trial of the experiment. So what actually happens? An event is a probability of a certain outcome. All right, so experimental probability, your booklet doesn't go into, and we're not going to go into too much, but just so you know, it's determined based on the results of an experiment. So experimental probability means that you're actually doing whatever it is that you're talking about. So it's measured by probability of A is equal to the number of successful results divided by the total number of trials. So for example, using a die, find the probability of rolling a 3 in 10 rolls. So we're going to go to the virtual manipulative on Mathigon, and I have this set up so that we can see we have a die and we have all the possibilities. So 1, 2, 3, 4, 5, 6 are the possible ways that the dice can be rolled. So we're going to roll it 10 times and see what happens. How often do we get a 3? So I'm going to roll and I get a 4. So I'm going to move one of my markers to 4 to just keep track. I'm going to roll again and then get a 2. And I'm going to roll again. So this, we are actually doing the experiment, and I got a 4. So this is our experimental probability. I got a 3. And I roll again. So we've rolled 4 times and I got 3 once. And I get a 2. Halfway through our rolls, I get a 5. Roll a 6th time and we get another 5. Roll a 7th time and we get another 3. Roll a 4th time. Sorry, we get a 4. Roll on the 9th time. And then our last roll, we get a 2. So our experimental probability is that we rolled 2 3s. We rolled 3 twice out of our 10 rolls. So that is our experimental probability for this time is 3 out of 10. Sorry, not 3. 2. 3 was our number. But our actual probability, our probability of rolling a 3 was 2 out of 10 because we only rolled it twice, which I could reduce to 1 out of 5 just to simplify my fraction. So, which is 20%. So 20% of the time we rolled a 3. And that was our experimental probability because we did the actual experiment. So then theoretical probability, and this is on page 21 of your IEL book, is when all the outcomes of an experiment are equally likely. So if we were to do it theoretically, instead of actually doing it, that's the probability. And this is often what we're going with, is because we're not going to do all of the experiments all of the time. So we have to do what is logically going to happen. So this, the probability of an event of A, is equal to the number of desired outcomes divided by the total number of possible outcomes. So for example, what is the theoretical probability of rolling a 3 on a standard die? So the probability of 3 is equal to the number of desired outcomes divided by the total number of possible outcomes. And so I have a net of a dice here, of a die here, that shows all the different outcomes of that we could roll when we roll a die, a standard die, which is 1, 2, 3, 4, 5, 6, right? We have 6 numbers. So our total number of possible outcomes is 6. And our number of desired outcomes, we want to roll a 3, and that's only once. There's only 1 3 on a die. So the probability of rolling a 3, the theoretical probability of rolling a 3 is 6. So even though our experimental probability was 1 out of 5, it happened more frequently than 1 out of 6. But in reality, if we were to do that a million times, more likely 1 out of 6 would be the probability of a 3 actually happening. We just did a small sample size, and so that's why they're not equal, which is also often true, which is why we use the theoretical probability opposed to the experimental probability, because we don't have enough time or capacity to do a million or 100 million trials in order to figure out what is likely to happen. So some common examples of that we use in theoretical probability would be rolling a standard dice like we just did. So it has 6 sides. So they can have pips on the dice, which are the dots, and they're organized in the same way so that you recognize a 1, 2, 3, 4, 5, 6 without having to count generally, but you can still count. Or you can also have dice that have numbers that have just the actual digits of 1, 2, 3, 4, 5, 6. This dot here is to show that this is the bottom, so that this is a 6 and not a 9. Just in case you have a dice that has more that goes up to 9 or 10 or above. So then still with rolling a dice, the theoretical probability is the number of events the probability of an event is equal to the number of desired outcomes divided by the total number of possible outcomes. That is still true when we're using dice. So here with the pips, so the probability of 5 is 1 out of 6, neither pips or numbers. The probability of an even number is going to be, well, our options are 2, 4, and 6. Those are our even values. And so there's 3 different ways that we can get an even number. And our total possible outcomes is still 6. So 3 out of 6, or simplified to 1/2, is the probability of getting an even number when you're rolling a die. All right, so another common example is flipping a coin. So it has 2 sides. We have heads or tails. Doesn't matter what kind of coin you use. We have heads or tails, whether or not what the images are. So heads are generally, for Canadian coins, the side that has an animal or a boat. I'm trying to think what all our coins are. Mostly they have animals. And so that's the tails side, and the head side is the side that has the Queen Elizabeth on it. And we can use that notation as H and T to simplify. So again, our probability is still the same, is number of desired outcomes over total number of possible outcomes. So the probability of getting a head is 1/2. The probability of getting a tail is also 1/2. There's only 1 out of 2 options. So then asking the question, what is the probability of flipping 2 tails in a row? Can we figure that out? We can't figure that out yet, but we will come back to this question. So because we don't know the number of total possible outcomes as well as the number of desired events. So we have to look a little bit more if we're going to do multiple rolls or multiple flips. All right, drawing a card is another common example of theoretical probability. So when they say drawing a card, we're talking about a standard deck of 52 cards with no jokers. So it has 4 suits, which are diamonds, which is red, clubs, which is black, hearts, which is red, and spades, which is black. And then we have 13 cards per suit. We have aces, 2s, all the way through 10s. Then we have jacks, which is J's, queens, which is Q's, and kings, which are K. Sorry, aces are 1 or A is how it's represented in a deck of cards. And so they're ordered from 1 up to 13 would be the king. And still, probability is still the same. Number of desired outcomes over total number of possible outcomes. It doesn't matter what we're talking about, it's still the same. So if we're looking for the probability of an 8, well, there's 4 8s in a deck of cards because there's an 8 of diamonds, 8 of clubs, 8 of hearts, 8 of spades. So there's 4 8s out of 52 because there's 52 cards. And then we can reduce that to 1 out of 13. The probability of a heart is, well, there's 13 of each suit. So there's 13 hearts in a deck of cards. So 13 out of 52, which is still the total number of cards. And then that reduces down to 1 out of 4, the probability being 1 out of 4. Then if we're looking for the probability of the king of spades, well, there's only 1 king of spades in a whole deck of cards. So it's 1 out of 52 because that's the probability. There's only one way that you can pick the king of spades. And then we also have a spinner is another common thing about probability. So it really depends on the number of divisions with a spinner because that is not generally defined. There's not a standard way. So we could have a spinner divided into 4 quadrants. And then in this example, we have the probability of desired out of the total number. So the probability of red is 1 out of 4 because there's only one way we could get out of the 4 different quadrants. Then we have another spinner. This one has 5 quadrants. So here the probability of green or purple. So we have 2 different ways that we could be successful. We could get green or we could get purple. And that would be 2 out of 5 of our total options. Or we have another one, which is a 3, which has 3 quadrants. And here the probability of blue is equal to 0 out of 3 because there's no blue. So no matter how many times I spin this, I'm never going to get blue. And so the probability is 0. It's impossible. So spinners can really be different depending on how you're dividing your spinner up. All right, so then another thing other than just generally how probability works is using tree diagrams, which you may or may not be familiar with in terms of figuring out multiple outcomes. So to start, here is a tree diagram for tossing a coin. So we're just flipping a coin, a 2-sided coin. It's not weighted, so that means that it's equal chance of getting a head or a tail. And so to draw a tree diagram, we first have branches, which are just arrows. So we have 2 branches because we have a head option and a tail option. And then we write the probability of each happening. So because a coin is an equal chance of 50-50 of getting a head or a tail, we would write 0.5, 0.5, or 1/2. You could write it as a fraction, or you could write 50%, whatever works best for you on your branches. And then you write the outcomes at the end of your arrow in terms of it's 50% of heads and 50% of tails of happening. And that's the basis of a tree diagram. We're going to draw more complex ones in a moment, but that's the parts of what it means for a tree diagram, what's going on. Okay, so let's extend this tree diagram to 2 tosses of a coin. Remember, we asked that question, what's the probability of getting 2 tails in a row if you toss a coin twice? So we're going to figure that out now. So our first flip, it's a chance that we get 50% chance that we get head or 50% chance that we get tails. I say 50% and it says 0.5. You can say it either way, again, because they're interchangeable. They mean the same thing. So then after we flip that coin, we get either heads or tails. Then we flip it again And for heads, if we got heads before, we still have a 50% chance of getting heads again. It didn't change it. Or we have a 50% chance of getting tails. Or if we flip tails on the first flip, we still have a 50% chance of getting heads or 50% chance of getting tails. It hasn't changed our probability. Now, even though we flipped it already, that doesn't change it. So we just keep tracking it. And now you can see these branches of our tree diagram extend out so that you can see it's sort of as it gets a little bit more complicated, as you get bigger and bigger, what happens. So then we can list all of our outcomes. So here we have head, head. So we could flip it, and on our first flip, we get a head, and our second flip, we get a head, head, head again. So that means that we call it a head, head. Or our flip, we can flip it first, get a head, and second, we get a tail. So that's a head, tail. First flip, we get a tail. Second flip, we get a head. So that's tail, head. And our third flip, or our fourth option is that we flipped tails on the first and then tails again on the second. And these are all the possible combinations that we could have. There's no other combinations that we could have if we just flipped a coin 2 times. So asking the question, what is the probability of flipping 2 tails? Well, we look and we see there's only one way that we can get 2 tails. We have to flip tails on both trials. So there's only one is our desired event, 2 tails, out of a total of 4 different options. Our total possibilities are 4 different because there's 4 different ways that we could flip it depending on those 2 points. So our probability of 2 tails is, or TT, is 1 out of 4 because there's one way out of 4 possible ways. So another question we could ask is, what is the probability of flipping 1 head and 1 tail? Well, if we look at our list of outcomes, we can see there's 2 ways that we get head and a tail. We get heads first and then a tail, or we get tails first and then a head. So there's 2 different ways that we could get the probability, get the desired outcome of 1 head and 1 tail. There's still only 4 different options. So the probability of getting a head and a tail is 2 out of 4 because there's 2 ways out of the 4 total ways, which is equal to 1/2. So it's a higher probability that you're going to get 1 head and 1 tail, then it's more likely than you're going to get 2 tails. All right, so let's calculate probabilities as well. So Alice is choosing a drink and a snack. She has 3 drink options: pop, juice, water, and 4 snack options to choose from: fruit, popcorn, cheese, and crackers, and a donut. Alice likes all of her options equally in any combination. What is the probability that she will have juice and cheese and crackers? So we're going to draw a tree diagram to figure out this probability. So first, our first thing that we're going to choose from is a drink. So we have 3 branches because we have 3 options. We have pop, juice, and water. Then we're going to put the probability. So the probability of each of those is 1 out of 3. Because it says she likes them all equally, it's not weighted. There's not more chance of one over the other. So we just say that it's 1 out of 3 because there's 3 options. Each one has 1 desired event. So then next what we do is we say, okay, now we have 4 snacks to choose from. So if Alice was to choose pop, then she would have 4 snacks to choose from, and she could choose fruit, popcorn, cheese and crackers, or a donut. And so those are 4 options after choosing a drink. And because there's 4 of them, the probability of choosing each of those is 25%, or 0.25, or 1/4. I didn't write a fraction just because it would be squished in. It's kind of squished. Tree diagrams get kind of squishy. So I wrote it as a decimal. Again, fractions and the decimals are interchangeable here, which might be hard to get used to. So if we have a pop, choose a pop, then we have 4 different options to choose from. The same, if we choose juice, we have 4 different options to choose from. If we choose water, we have 4 different options we can choose from. So you can see maybe why this is called a tree diagram, because it's getting more and more branches and getting more and more wide and potentially looking more and more like a tree than before. Okay, so this is our full tree diagram. We have our first choice of pop and our second choice of a snack. You could do this in reverse. You could have done the snack first and then the pop, or then the drink. that would have been fine. Your diagram would look slightly different, but your answer should still be the same because the probability is still going to be the same whether or not you choose your snack first or you choose your drink first. Okay, so then answering the question, what is the probability that she will have juice and cheese and crackers? So we need to follow that pathway. So we say, okay, so juice and cheese and crackers, is there any other way that we can get this pathway? No, there's only one option. It's only juice and then cheese and crackers. None of the other pathways are going to give you that option. So the probability of juice and cheese and crackers is equal to the probability of choosing juice times the probability of cheese and crackers. So the probability of choosing juice is 1/3 times the probability of cheese and crackers, which is 1/4. Here I've written it as a fraction, or you could write it as the probability of juice, which is 0.3333 as a decimal, times the probability of choosing crackers, which is 0.25. So either way, you're going to get the same answer. So then you multiply those two together. So then the probability of choosing juice and cheese and crackers is 0.08333, or is equal to 1/12. Once again, the fraction and the decimal is the same value, the same amount. So you could use either one. You don't have to do them both at all. You could just do it as a fraction or just do it as a decimal. It's totally fine. I just wanted to show you the different options. So the probability that Alice chooses juice and cheese and crackers is 1/12 because there's only one pathway out of all of the 12 pathways. But that's how you do it with your calculation of your values instead of just using the tree diagram. Okay, so let's do the same thing without using a tree diagram because you're probably not going to want to draw a tree diagram every single time. I know I don't. So let's try to figure out a probability of something with multiple trials or multiple choices without drawing a tree diagram. So Francis rolls a 12-sided die 4 times. So this is what a 12-sided die looks like. This is half of it. And then there's the same shape on the other side. So it has pentagon faces, and each from 1 through 12. So what is the probability of getting an even number for all 4 times? So we're going to roll the die 4 times. So if we were to do that, we would draw a tree diagram. We'd have 4 different levels, which is a lot. We don't want to do that. So how else can we do it? With just calculating. So the probability of 4 even rolls, so meaning that there is 2, 4, 6, 8, 10, or 12 are all your even numbers, is equal to the number of desired outcomes divided by the total number of possible outcomes. It is still the same. So what that means for this one is that the probability of 4 even rolls is that the probability of the first roll is even times the probability that the second roll is even times the probability that the third roll is even times the probability that the fourth roll is even. So that means that the probability of 4 evens is 6 out of 12 because there's 6 evens out of 12 numbers times 6 out of 12 times 6 out of 12 times 6 out of 12. So we're doing it times itself 4 times because we're doing 4 rolls. So that equals 1,296 divided by 20,736, which is simplified to 1 out of 16. So if you were just to multiply these out, that's what you would get. Or you could reduce them to either a half or to 0.5, if that seems simpler to you, and do 0.5 times 0.5 times 0.5 times 0.5. And that means the probability of an even number is 0.0625, which makes a little bit more sense to me. I don't really know how big 1/16 is, but 0.0625 makes me think, well, this is going to be like 6%. And I can see that from the decimal. And if you were to use a calculator, if you do 1 divided by 16, you're going to get 0.0625. They are the same amount. They're just in different ways. So again, this is why it's important to remember that fractions and decimals are the same depending on what is useful for you. So it's only 0.0625 chance that it's likely that out of rolling a die 4 times that we get an even number each time. All right, so now if you want to pause the video and do the support questions on page 22 and 23, questions 1 through 6, those are all the questions that we've covered. And we'll go on to consolidate what we've learned today and do some practice problems together. So for lesson 19, the highlights are for theoretical probability. Our first, the terminology. So we had successful result, trial, sample space, outcome, and event all are. We also have to know that theoretical probability is equal to the number of desired outcomes divided by the total number of possible outcomes. We have to know what tree diagrams are and how to draw them. So they display all events by using one branch for each possible outcome, including the probability. So we have both that probability information and also the outcomes on a tree diagram. To calculate probability, when determining the probability of multiple events, we multiply the probabilities of each event together. So for success criteria, our first we have that we can calculate the probability of a desired event. So using our theoretical probability is what we're doing because we're calculating it. We're not actually doing the experiment. And two, we can use the probability terms accurately. So hopefully by listening to me, by talking with me, and by reading these pages in your booklet and through the lesson, you're comfortable with the terms. And then finally, you're comfortable with probability represented in various forms. So like I've said throughout this lesson, sometimes using it as a percentage, a fraction or a decimal may be useful depending on what you're doing. So being comfortable that those are interchangeable or displaying it as a tree diagram or not is really important so that you're comfortable with all the different ways probability can be represented. All right, let's do some practice problems. So a pet store has 10 cats, 12 dogs, and 3 turtles. If Haley randomly selects a pet to take home, find the theoretical probability of getting A, a cat, B, a turtle, or C, a dog and a turtle. Or a turtle, sorry, a dog or a turtle, not and a turtle. So we have a total of how many animals to figure out our total possible outcomes. So our total is important to know, is equal to 10 cats plus 12 dogs plus 3 turtles. So that means that our total possible outcomes are 10 plus 12, which is 22, plus 3 is 25. So there's 25 animals to choose from in total. So the probability of getting a cat, so the probability of C, is equal to the number of cats, successes, those are the successes, would be cats, out of our total amount. So I'm going to just write that out so that we get used to it. Number of cats out of number of pets, those are our total outcomes. And so the number of cats is 10, and the number of pets is 25. So it's 10 out of 25. Well, I can see these are both divisible by 5, so I can simplify my fraction. 10 divided by 5 is 2, and 25 divided by 5 is 5. So 2 out of 5. Reducing your fraction, while not essential, is really helpful because it might make it into something that is a little bit more friendly or easier to understand. Okay, so then the probability of choosing a turtle. So the probability of T, a turtle, is equal to the number of turtles over the number of pets, which is equal to, well, there's 3 turtles at 25. And 3 is a prime number, so I know that I can't divide 3 by anything but 3 or 1 evenly. And 25 is not divisible by 3, so that means that that's as low as possible. So 3 out of 25, opposed to 2 out of 5. So it's more likely that we're going to choose a cat at random than a turtle. And then the probability of choosing a dog or a turtle. So that's the number of dogs plus the number of turtles. Those are all options, right? Because it could be either one, all divided by the number of pets. So the number of dogs is 12, the number of turtles is 3, so that's 15 out of 25. Again, these are both divisible by 5, so 3 out of 5 is the probability of choosing a dog or a turtle. And that's how you can do it like that. You could draw a tree diagram, but you can see that this is a little bit more succinct or straightforward to do it this way. All right, number 2, using a standard deck of cards, calculate the probability for the following situations. Based on an experiment of drawing 1 card from a well-shuffled deck, what is the probability of drawing a red card from the deck? So we remember the red cards are the diamonds and the hearts. And there's 13 diamonds and 13 hearts. And remember, a total deck is 52. So the probability of getting a red card is equal to, well, 13 plus 13 is 26. So there's 26 red cards out of 52 cards in total. Well, which is half the deck. So it's 1 out of 2. And over time, you get used to these, become more familiar. So what is the probability of drawing a heart card from the deck? So we remember that there are 13 hearts. So the probability of a heart is going to be 13 out of 52, which is going to be 1 out of 4. It's a quarter. What is the probability of drawing an even numbered card? So of any suit from the deck. So we have 2, 4, 6, 8, and 10 are so there's 5 options, but there's 5 options for diamonds, 5 options for hearts, 5 options for clubs, and 5 options for spades. Sorry, my spades, my drawing isn't amazing, but you get it. So that means that there's 5, 10, 15, 20. So the probability of drawing an even number card is 10 out of 52. They're both, because there's, sorry, was it 10? No, it's not 10, it's 20. That's why it's important sometimes to track what you're doing so that you catch yourself. So it's not, it is equal to 20. There's 20 different ways, 5, 10, 15, 20 different options that we could pull out of the 52 cards. So both of these are divisible by 2. So I can see that, so it's going to be 10 over 26. Well, both of these are still divisible by 2, so that it's 5 out of 13. So the probability is 5 out of 13 of getting an even number card from the deck. And then what is the probability of drawing a face card from the deck? Well, the face cards are the jacks, the queens, and the kings. So there's 3, and there's 4 suits, right? There's the diamonds. So 3 for the diamonds, 3 for the hearts, 3 for the clubs, and 3 for the spades. So that's 3, 6, 9, 12. So the probability of a face card is 12 out of 52. And again, both are divisible by 2. So 6 out of 26. Both are divisible by 2. So then 3 out of 13. And there we go. That's how you could do it if you're dealing with a standard deck of cards. All right, number 3, I want ice cream. The ice cream shop has the following choice. You can choose a cup or a cone. You can choose vanilla or chocolate ice cream, and you can choose sprinkles, nuts, or berries. So assuming that you choose one of each of those that you pick, you don't just have a cup of nuts. You have to pick one of each of those 3 categories. Draw a tree diagram to show all the options. So first, we're going to choose either a cup or a cone, and you're going to see how it's easy to get squished once you start going. And the probability is 0.5 for each of those. It's equally chance that we get either of these. There's 2 options, so it's 0.5. It's 1 out of 2. Then we could choose either vanilla ice cream or chocolate. So if we chose a cup, we could choose vanilla or chocolate. And again, we have 0.5 chance because there's only 2 options. Or if we chose a cone, we could choose vanilla or chocolate. Still 0.5 for either option. And then for our third choice, we could choose either sprinkles or nuts or berries. And it's 0.33 or 1 out of 3 for each of these options. And the same for chocolate. So this is where you start to see that your tree diagram can get a little squished, and I've never figured out how to guarantee that you're not going to get squished. It just always happens to me. So yeah, if we chose chocolates in a cone, we get sprinkles, nuts, or berries. And it's still 0.33 for each of those options. And then if we chose a cone and vanilla, and then we have sprinkles, nuts, or berries, and it's still 0.33 for each of those options. Or if we chose a cone and then chocolate, we can have sprinkles, nuts, or berries. I spelled nuts wrong. It's still 0.33. When you're doing this for your work, I don't expect it to be perfectly immaculate. Just make sure that it's legible so that I can understand what you're doing. Okay, so that's a tree diagram, and maybe give yourself more space than I did. So how many different combinations are there? So each pathway is a different combination. So we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 different combinations. How many combinations would there be if the ice cream shop added another flavor? So if we add another flavor in here from 2 to 3, so we think about it, we'd have 2 choices, now 3 choices instead of 2 choices for the ice cream flavor times 3 choices. Because this one, if we look, we have 2 times 2 times 3, which 2 times 2 is 4, times 3 is 12. So 2 times 3 times 3, if we increase an ice cream choice. So 2 times 3 is 6, 6 times 3 is 18. So we don't have to redraw our tree diagram. We can just think about what logically is going to happen. So there would be 18 if they added a flavor choice. Okay, so then how many combinations can Jane get with vanilla ice cream? So we're going back to our tree diagram and we see, okay, well, if we get a cup and vanilla, then we still have 3 options. And if we get a cone and vanilla, then we have 3 more options. So there's a total of 6 combinations that we can get with vanilla ice cream. How many combinations can Jane get if the ice cream shop runs out of nuts? So if we don't have the nuts, we get 1, 2, 3, 4, 5, 6, 7, 8. So there's still 8 combinations. And how many combinations can she get with chocolates and strawberries? So if we want to have chocolate ice cream and strawberries, well, we go and berries, we can go 1, 2, because we either have a cup or a cone and chocolate and berries. So there are only 2 combinations to get chocolate ice cream and strawberries or berries. So then let's go back quickly. We have a little bit of time and figure out what the probability of this happening. So if there's a total of 12 combinations, so the probability of choosing vanilla, well, there's 6 combinations out of a total of 12. So that means that we're using the original with only chocolate or vanilla. So that means that it's 1/2 of the probability of choosing vanilla is 1/2, 50% of the time. So then the probability of getting, if there's no nuts, so then how many options does she have? So the probability of getting it without nuts is 8 out of 12, because there's 8 different combinations. So 8 out of 12, 8 divided and 12 are both divided by 4. So we can get 2 out of 3 is the number of ways that could happen. And the probability of chocolate and strawberries is equal to, there's only 2 combinations, so that means that it would be 2 out of 12, which is 1/6. So the probability of getting chocolate and strawberries is 1 out of 6 overall. So that's how you use the combinations of looking at your tree diagram to figure out. You could also use your values. If you didn't have a tree diagram, or if you didn't want to count, you could say, okay, well, the probability of getting vanilla is going to be 0.5 times 0.5 plus 0.5 times 0.5. And that would give you a quarter times plus a quarter, which gives you a half. So you can use either just a tree diagram, or you can use the combinations, the probabilities. All right, so that's all that we have for today. So as always, if you have any questions or concerns, if anything isn't making sense, please let me know. You can call me at the main office and leave me a message at 807-737-1488, or toll free 1-800-667-3703. As we're working remotely, it is best to leave a message there and telling me when it would be a good time to call you back, so that we don't continue to play phone tag back and forth. That's the easiest thing to do. Or sending me an email, and we can either organize through email a time to do either a video chat or a phone chat, if that would work as well. My email address is bronwyn.slate, which is spelled BRONWYN.SLATE@nnec.on.ca. You can always connect with me through Facebook at bslatewahsa, and my YouTube channel is also bslatewahsa, where this replay will be posted up this afternoon shortly after airing. Thank you so much for joining me today. Which